When deploying massive enterprise systems, treating application security as a simple starter dependency creates an immediate, silent liability. Relying exclusively on high-level method annotations, like @preauthorize, without understanding the underlying execution mechanics, leaves your architecture heavily exposed. The framework is not an opaque utility that automatically shields your endpoints. Instead, it operates on a highly complex, layered infrastructure of native servlet proxies, strict interceptor chains, threat-local data storage, and polymorphic authentication provider networks. To secure an application properly, you have to track the exact physical path an HTTP request takes to bridge the gap from a raw external web server directly into the framework's internal memory space. We are going to map the chronological execution order of the core web filter pipeline, step by step. We will then look at exactly why standard security configurations catastrophically crash inside modern, high-concurrency reactive environments. Treating framework security as a black box guarantees silent permission drops, leaked credentials, and cascading authorization failures in production. This diagram illustrates the physical separation at your backend's core. Apache Tomcat operates entirely outside the Spring application context. To bridge them, Spring inserts a standard Servlet component named DelegatingFilterProxy into the external container. This component contains absolutely no security logic. When network traffic hits the server, this proxy intercepts the execution stream and performs an internal target name lookup. It then routes the raw data stream directly across the container boundary and passes execution control into a Spring-managed component called the FilterChainProxy. The FilterChainProxy serves as the core framework engine. It evaluates incoming URI patterns against your configuration to select the precise sequence of security filters the request must traverse. This handoff physically connects external network traffic to internal framework logic without violating standard Servlet API specifications. This visualization displays the vertical stack of 6 discrete filter layers. An incoming request must survive this sequence. First is the security context persistence filter. It intercepts the request, loads an existing security context from a persistent store, and binds it to the active execution thread using thread local. On its way back out, this first filter must completely clear the thread context to prevent critical cross-thread data leaks. The packet then hits the second layer, the CSRF filter and course filter, enforcing cross-origin constraints. They verify cryptographic state tokens to block cross-site request forgery exploits on mutating requests. The third layer, the logout filter, explicitly intercepts logout requests, destroys active session tokens, clears the security context, and handles redirection. These first 3 layers act as the essential state management perimeter. They ensure the request is physically clean and properly bound before any user credentials are evaluated. The packet reaches the 4th layer, the username-password authentication filter. It extracts raw credential variables from the headers, packaging them into a standardized, unauthenticated token block. The 5th layer, the exception translation filter, operates safely as a tactical catch block wrapper, performing zero-independent security validation. Instead, it catches downstream security exceptions. An authentication failure triggers a login challenge, while an access denial returns an HTTP 403 forbidden status. Finally, the packet hits the 6th layer, the filter security interceptor, the ultimate authorization gate immediately before the dispatcher servlet. This gate reads the now authenticated token out of the thread context. It evaluates requested URL mapping metadata constraints against explicit authorities granted to that token. If the roles do not perfectly align, it throws an immediate exception and blocks the request from advancing. By enforcing this rigid chronological sequence, the framework ensures every HTTP request is rigorously sanitized, credentialed, and authorized before it touches your business logic. To verify credentials, the token structure splits into 3 fields. First is the principal, the unique user identifier. Next are the credentials, which are typically nullified post-authentication to prevent theft. Third are the authorities, mapping out explicit action permissions. The filter submits this unpopulated token to the provider manager. It loops through a collection of independent authentication provider instances, polling them until it finds a structural match for the specific credential type. The selected provider executes the validation loop, querying a database and validating the password hash. Upon success, it constructs a brand new, fully populated, authenticated token and passes it back up the chain. This decoupled delegation network allows engineering teams to infinitely scale and swap cryptographic validation methods without ever having to alter the core web filters. That entire standard architecture works flawlessly under one condition. It relies completely on the mode thread local storage strategy. Look at the diagram here. On the left, this default strategy operates on a rigid assumption that one single request executes sequentially on one dedicated operating system thread. Modern architectures leverage non-blocking reactive stacks like Spring WebSlux. Tasks execute asynchronously, hopping across event loop threads. When execution switches threads midstream, it loses access to the old thread local storage. The token vanishes. As a result, the application experiences unexpected, intermittent authorization failures. Security permissions drop randomly under heavy production load. To survive this environment, senior engineers must completely abandon thread local configurations when building reactive microservices. Integrate security configurations directly with the Reactor Context API. The Reactor context does not bind to a thread. It travels alongside the data stream pipeline. This enables interceptors to safely read tokens across asynchronous boundaries without data loss. Application security relies on an intricate network of context boundaries and interceptor sequences. Mastering these internal primitives is mandatory for writing resilient, enterprise-grade architectures that survive intense industrial loads.